is interested in design research and as well in process that feed in this research, basically. So here is Jonas. Half an hour, be sharp.
Yep. Okay. Thanks, Claudia, and thanks for the invitation. And thanks to everyone attending. Closer. Can you hear me? Okay, so I'm going to present two projects done in CHETS, which is a design and research collaborative based in Stockholm. The partners, the founding partners of CHETS, besides myself, are Daniel Norell, Pablo Miranda, and also Ulrika Karlsson, who's a principal of Servo, who will present later, and Marceline Gao, as well, a principal of Servo. So I'll present two projects, and my ambition is to really look at the development of these projects. And my reading actually of the architecture machines part is really how these performative aspects of machines or devices are actually very important during the development of the projects as well, as sets of prototypes or devices that kind of converge through this process. And we work in different media during the development, so there's sort of a remediation going on between them. And finally, they come together in projects which also carry these capacities in different ways. So just briefly around the way these projects were conceived and developed, we'd like to see them as innovation-driven design projects in the sense that, to certain extents, we were not at all aware of or had decided on the outcome of the project. We were starting in different interests and going through a number of almost exercises during the development, and slowly the projects were formed. The notion of the prototype is really important to us and to me personally, as a number of different platforms or settings that are linked up. And the prototype is not really just the final thing, a final functional piece. It's actually a system or a set of rules, digital model, or similar things. And most importantly, we're also very interested in notions of production, how to actually produce physical environments in different ways. And we're looking at different principles that may have not been used so frequently, picking, of course, expertise from other fields very much. These projects are also fully documented and presented in my recently completed licentiate thesis, which is available in the AA library. So you're more than welcome to take a look at that. Well, the first project is called PARCEL, developed by myself, Pablo Miranda, and Daniel Norell. And the project started in an interest in disposables and different production technologies, such as the ability to print electronic conduits that's already abundant in the medicine industry, for instance. Also off-the-shelf electronics, like the RFID tag and other things that makes it possible to put in a very cheap way intelligence into final pieces. And in addition, also programming, the programming of behaviors rather than forms, maybe. So the programming of characteristics for an environment in different ways. So we started with a number of prototypes, of tests that slowly were coming together to form the project that we later named PARCEL. So you can see the interest in disposables, which was actually part of us being kind of tired of the pristine object of the 3D print or the CNC mill, but actually looking at other kind of material capacities. And in a way, all these different loops and trials become, in a composite way, a project in the end, which in itself we think have several layers of operation, of performance, and so on. But to us, it's really as important to look at the individual parts of the development. And in this sense, we really think of it as a continuous research in which we can pick a part of a former project and learn from that. So in PARCEL, one of the starting points, as mentioned, was the idea of the disposable or the printed product, really looking at the paper industry and printers and so on, and basically starting with a sheet of paper and folding it. And after a number of trials, finding certain almost structural capacities through this folded line. And these forms were then connected to the pattern for actually fabricating something. So an important principle of the formal development of this thing, which at a certain stage we start to conceive as a wall paneling system, an interior space paneling system. We kind of like the idea that, that we could work at scale 1:1. We could actually work with a sheet, start to fold that, and obviously also testing different variants in digital modeling. But we would have the immediate pattern for actually producing these objects. And in the same kind of template that we developed, we would have information for obviously cut lines and fold lines, but also how to print an electronic network that would allow us to put a single microprocessor in each piece to provide a certain intelligence, and other components to pick up sound, to emit light in different ways. Also the actual detailing of putting things together, and how they also served doubly as connecting an electronic network between different parts or units of the project. So this is the same kind of tool used by IKEA and others to produce millions and millions of plastic sheets. And we were kind of interested in this because the production of it actually is using, for instance, laser cutting to create an initial score in a board, a timber board, and then putting in blades, obviously directly based on our digital model. But it came with a low initial cost, so the economy of the project became kind of viable as well. We could have moved toward a situation, and this was really a consumer object. And this is the piece as produced with components sitting in place. The thing we wanted to explore here was also then the ability to actually print electronic conduits, but the complexity of the project allowed us to test certain things. We're using conductive tape in combination with glue and paint to actually fix electronic components on the plastic sheet, which is detailed like this. So this is the speaker unit, which is not soldered at all, but actually glued in place. And the folded unit, So in this way, the idea of, or notion of the title of the project, also PARCEL, was important because, first of all, it's like a small package, right? It's partially folded up into a small unit, in which all these different components act out also as aesthetic properties and becomes patterning in different senses, but it's also very instrumental patterning in the sense that it actually provides the electronic network for the behavior that I'll show a bit later. But also the direct relation to the pattern for making it, with this unit now sitting on top of just a print of the actual template for it. So we did 3 variants of the formal principle in this case to be able to produce a variety of combinations, and they in return could provide us with 6 different units by mirroring the plastic used. So these are the 6 parts of the project. But all these exercises were really about us linking it to a production aspect to be able to produce the units. And as we sort of came close to the idea of a consumer object that would be possible to buy at a museum store or anywhere, it's also the fact that you could collect it, you could recombine them. So the whole build-up of the project allows a user or a visitor to actually reshuffle the order of how these pieces are combined. So the exact curvature of the piece makes certain combinations possible, but others are not possible to actually make. At a later stage, which was really part of my thesis, I returned to the project and started to look at more parametric variations of it. The whole production line was already developed, but it was kind of interesting to me to actually to go back and redefine certain things, while the panel would keep its almost topological build-up, the same kind of principle for curvatures and so on. We could then instead develop a whole range of different variations between the pieces, which is sort of a later adaptation, which would need another production method. In this case, using directly laser cut sheets to fold up the panels. And then in this sense, creating variations and differentiation across a panel surface. And this became also a quite clear example of certain principles of notions such as design solution spaces, which is really the whole range of variation that a single designed piece could take, which is something I made quite good use of in my thesis as a clear examples of these things. But there were also other investigations going in parallel. This is simply modeling the electronic network, which is actually the simplest way to connect all these pieces up, and still to allow us, and we really, to our surprise in a bit, this very ornamental characteristics came about. And also parallel studies of or simulations of the connectivity of the panel, in this case using the open source software processing to actually make a real-time model which would use the same algorithms to control the different parts, and we could see how information would be spread across the whole panel. Another aspect which was quite interesting and something we were quite unused to is that we could actually, or had to, test certain parts of the project. Basically just the fact of seeing if an LED would actually light up or not, which sounds really mundane, but it really was required all through the project, and each individual piece had to go through a testing to see if it actually held. And this is sort of a result of the fact that we were interested in exploring parallel things at the same time, and in many cases we could really only achieve partial success in the functionality of the projects from the basic fact that all these materials combined to a certain kind of a composite interlaced product that had to work all together and was developed in a very short time, including the way it was actually produced by using glue instead of soldering because of the use of plastic. So I'm just going to show a little bit of how now we have some sound on this. So what happens in the panel is that there are microphones spread all across its surface in certain units. They pick up a sound and they interlace it with a white noise, a signal, and then they distribute it to all its neighbors in all four directions. And each neighbor would sort of reprocess that signal and send it, continue to send it away. And if it would be a unit with an LED light, it would also emit that light before transforming it again. Or with a speaker, it would emit the sort of a generated noise coming from the initial signal. So the idea was really to be able, for instance, to pick up a conversation, and that would sort of spread over time across the whole panel, being transformed and not legible at all anymore. But instead creating local ambiances and effects across the panel. So I think I'll skip that for now. And the project was actually presented first in the Stockholm Concert Hall, which is a 1920s building in central Stockholm, which has certain key, and it's a very special place. The panel in this instance was site-specific in the sense that we actually picked up the color of the wall, which is a very beautiful and very differentiated color surface. But this is actually more of a contemporary play on that. So we wanted to play obviously with the shadows, but also the kind of surfacing from sort of a glossy to a more matte surfacing. And in the end also playing with the ornaments that were already there. So we sort of mimic the ornamental parts on top of this wall in our more instrumental electronic network. It was later also presented at Lunds Konsthall in this more clean way to more of a model presentation, in which we used printed surfaces to actually give the idea of a large-scale panel system. So this project gave us also a commission from Vitra Design Stiftung in Weil am Rhein, in which we were asked to participate in an exhibition called Open House. They had the idea to explore the influence of technology really on the home environment, but not in the sense that having communication between a toaster or a fridge or be able to control your environment, but actually look for the more ephemeral and atmospheric effects that these things could have. So in a way we were asked to either again present the old project, or we had the opportunity to do a new one, but that was sort of a given scale, and we knew that we would operate in a domestic environment, so we really felt to pursue some of the things we explored in the previous project. In this case, our first interest was actually in shape memory alloy, which some of you may be aware of. It's, for instance, the little metal muscle used in the Mars rover up to the left to actually clean the solar panels. So it's typically used in robotics to have really low maintenance, long-lasting kinetic actuators that can actually move things. So that's the starting point, and we had no idea at that point what we would actually be moving. This is the first instance or the first prototype developed by Pablo Miranda. It's actually a small little device, or almost a creature, that rearranges itself to avoid shadowing the light sensors on the wall behind it. And again, it's controlled by a number of individual intelligence units, small microprocessors that actually communicate with each other, with each other to almost have sort of an emerging behavior that's the result of the individual units. But then obviously in this project there was a lot of tests and trials around how we can use this material in a very simple way. Basically mechanics, trying to understand the forces involved, how we could actually trigger them and so on. And we also continued the idea of the wall paneling system. So quite soon in this project we set up a certain configuration that we would be exploring, and tried to find the proper tools and environments to actually simulate these behaviors. This is parametric models trying to look at different deformations of these panels. So it's a parallel test of the mechanics of it, but also how it actually would behave and perform, and how you would experience the resulting project. Obviously also a number of models to actually explore these. And what we were really interested here is not the fact that that thing up there could become that, but what would actually happen in between. The actual performance of these deformations that we could not really control, but actually would be emerging or being the result of a number of different forces. And hence also the name spline graft, which is really the spline or the ridge, which is a result of a folded panel, which is in continuous movement. It's actually quite similar to how aircraft were steered in the early 20s, in which before you had proper, you would actually torque the whole wings to make a plane roll. which is something that we found quite fascinating. And in this case, obviously, there would be the need for a structural system also to hold this panel. And in a weird way, the development of that structural system became even a larger part of the project than the panels themselves. So it went through a number of iterations to actually define a panel, each step being a refinement of the previous one or taking a different route. But also looking for a componental approach here in which each of these units would actually carry its own intelligence and be part of the emerging complete behavior. So this is the final outcome of that, which is basically a structural system with interlaced other systems. So it's really about the structural capacities, the mechanics, the network of electronic conduits, everything produced in a similar way, and it would be carrying the panel. And the idea is also that this whole thing could be configured manually, so these different overall shapes is not something that's deformed in real time, it's actually a setting of the system. And the dark part is actually the panel, which would be deformed. And obviously also an electronic network, the conductive parts that actually make this possible, with a central unit distributing power to the different parts, which would each have a shape memory alloy actuator, or two of them actually, to shift this clutch to induce movement. Again, trying to simulate the behavior by using a processing again, in which we could run the same algorithm that we'd actually use in the final piece. So these are stills from a real-time rendering showing the deformation going on in the project, in parallel with more traditional representations to actually understand the deformations in different ways. And this is really the mechanics of the whole project. We decided to use a polyurethane panel, which is also sound proofing, and has certain characteristics of almost self-supporting or structural as they are folded. But we're kind of interested in the fact that the actual form was not part of the design. It was the result of this folding movement, and in the end, actually, of the actuating mechanisms and how they were controlled by the local intelligence. Again, a series of physical prototypes to test the structure, to see how it all comes together, and also finding a good way of production. In this case, CNC milled acrylic plastic parts with inserted engravings for wiring, and nickel brass conductors that actually make sure that we can bolt them together and get electronic connection between each unit. These are the 5 different parts of the structural system, and we were kind of again interested in the way how these ornamental effects came about. In this case with the wiring itself. The exhibition also, it's a traveling exhibition, so it needed to be transportable. We need to find a way to actually fold the panels. This case using Velcro, so you could fold up one of these crease lines, and it could be unfolded again and rolled up. This was actually the most difficult thing to fabricate, working in soft plastics and convincing producers actually to take on something which we thought was really, really simple, to make these engravings in the plastic, but to them was a very difficult thing to do. But this was a much more simpler technology, really etching away nickel brass conductors, which would give us the metal parts that allowed us to put everything together and be conductive. This is the shape memory alloy in itself, which is, as you see, a very, very thin wire, in this case set in a protective Teflon tube. The thing with it is that it responds to heat. You're probably all aware of that. We decided to control that by electricity So it reaches about 100 degrees Celsius, and we needed the covering parts for it to actually not damage the rest of the project, but also to work fully mechanically. So the project as set up was really ambiguous in the sense that the whole hidden structure was in a way more interesting to us than actually the panel in itself, which I think this is sort of a part of the work we've done, is that we can put a lot of effort into things that are actually invisible, but we also like to actually design them for visible effects. And this is really showing how all parts come together and the bolts actually joining the pieces to also provide the electric conduit network. And one of the actuating mechanisms as inserted, and with the shape memory metal to control it. This is in place in the open house exhibition, which opened a few years ago in Essen in Germany. And how it was set up. And this is also a crucial part of it. The reason for this being pretty bumpy, this panel, is actually that all these things came together, obviously, in the very last minute before the opening, in which we actually realized that while we can control each part, when we put the full power on, the electronic circuits actually could not stand the heat. So it's really about developing so many things in parallel that you can't really control the whole project in full. Still, all the individual parts are quite interesting to us. In the end, we actually set it up with partial panel and the actual structural racks being more visible and presented in parallel to a visualization. But I'll show this little animation here also, and some shots to show the effect. There's no sound on this one, which is also one of the reasons we chose the actuating mechanism, because it's completely silent. And in fact, also the project runs on, it's triggered by movement in the space. So there's a genetic algorithm which is continuously storing whatever kind of activity is going on. And if it performs a behavior at a certain point in which there are many people visiting the space, it registers that as a very successful movement and stores it. And it tries to then to merge and evolve a more successful movement by combinations of previous behaviors. So in a sense, it would, for a lifespan of about 2 years, working daily, it would evolve into something which it would think would be the most popular way of actually behaving, which in a way could possibly end with the project being completely still, if that was the case. So this is actually the wrap-up of the presentation. I think I was very short, huh?
Me lo abbassi un po'.
Sì, arriva, ma non so dove è questo. Where's your sound going? Sound is in front? Yeah, I know, but look at the table. Look, adesso. Can you put your sound really nice and low?
No, non si vede.
Can you put your sound low?
Sì. One second, Ok, lieviti un po'.
Okay, well, just put your sound. That's it. That's fine. That's fine.
Okay.
I'll sort it out.
Okay, we have the last speaker after in the morning. That basically it's me, Claudia Pasquero, and Marco Poletto. We are co-founder of Ecologic Studio in London and tutor of Inter 10 at the AA. So we are in both category. We are both at the AA than in Universe. We are in a privileged position in this sense. And we will present STEM Cloud, which is somehow an architectural oxygen making machine. STEM has been developed through a series of installation in which evolved its geometry, shape, and this also is meaning in a way. Was first conceived for the London, at the time called London Biennial in 2006, then presented in Venice both in 2006 and 2008. And finally, this version was developed for the Seville Biennale this October. Okay, so yeah, the first question, can machine make architecture? Okay, I borrowed this picture from a friend that posted in Abitare to advertise the event on the Abitare website. And without discussing the ironic meaning probably of these pictures, I would like to substitute the question with, can architecture be imagined and designed as a machinic system of communication, exchange, and artificial evolution? And in this way, I would like to introduce how we intend architectural machine. We intend architectural machine, we call it eco-machine. And with eco-machine, we don't intend machine which are sustainable, but we intend artificial device that try to engage in a dynamic way, in a dialogue with the context. Marco?
Yes, maybe just very briefly want to introduce Ecologic Studio, which is practice we created in 2004, and the way Ecologic Studio works is kind of simplified in our website. Basically running in parallel on sort of 3 different levels, if you want, which is a kind of more commercial-based projects, which you find in the project section, and what we define kind of research project, which is part of what we are going to introduce today, and then obviously a sort of academic work, which has to do with a series of workshops that we've been organizing around the world, and obviously our unit Inter 10 here at the AA. Obviously the 3 sections are by no means segregated, but actually the idea is to create as much as possible interaction, interference between these different domains, and that basically what we have been trying to do in the past. To probably help define a little bit the idea of eco-machine and how it came about, we can just briefly show you a couple of other installations that have been developed along the line, although with very different materials and conditions. And this, for instance, is a kind of project which has been generated within the AA with a visiting workshop, was called Fibrous Structures, which then got let's say implemented in a 2 months long installation in Garanti Gallery in Istanbul. And basically the real key of this project was to explore how a sort of diagrammatic way of manipulating material could become a generator or a trigger into actual new material structures, new material properties. And in this case, concrete was the actual material used. And this is just a really quick video showing on how, by working with Lafarge, in this case manufacturer, we actually managed to develop a superfluid concrete, which became really a way of interactively actuating or materializing the structure. In this case, the machine, in fact, is at different levels, we can say. It's a diagrammatic machine, as you can see on the top. Is a kind of construction machine, which then becomes space, and then eventually is all the kind of machinic properties of the concrete. You want to add something about this? Maybe just quickly want to show you another example, which I think is quite interesting in this case, and then we just go through the main project today, which is the one presented in CV. This was a kind of site-specific installation called Aqua Garden, presented in Milan 2 years ago. And I think, again, what is interesting is how the sort of machinic qualities come from a diagram or a logic, in this case a branching logic, and on the other side a specific site or a specific local environment, which is the typology of the Milanese courtyard and the kind of microclimate of the summer, of the Milanese summer. And then effectively the combination of the two gave rise to these experiments of rainwater collection and then percolation. So the actual fibrous structure or branching structure became really a kind of a mean to liberate certain properties, certain climatic conditions that are latent, if you want, in water, but somehow not manifested in traditional or conventional water collection or rain collection systems. So again, the idea of a garden being materialized through a kind of machinic device. Yeah, it's okay. Okay, so let's go back to our main presentation today, which in fact is about yeah.
So this instead is the diagram that we use to somehow conceive STEM as an ecosystem, and to try to understand how the different components of this self-regulatory screen or oxygen-making machine are related one with the other. We call this diagram cybernetic diagram and create a relationship between behavior, machine, and environment.
I think in this sense we should probably connect with something Theo was mentioning before, the kind of interesting tradition which spans from the word of cybernetic, but then has been, let's say, expanded, particularly here in London. People like Gordon Pask, together with C.D. Price and John Fraser here at the AA, whereby the attention has been put not only on the actual interaction itself, but on the possibility of interaction to generate communication. And that particularly by paying attention to the flow of information, which is what this kind of diagram try to exemplify. That's why we sort of chosen to somehow organize the presentation, but also the way we work on the project from the point of view of the communication between different layers and the information that flows from one layer to the other.
Yeah, it's okay. In terms of control, communication, and as well in terms of the subject that created the project, I got quite interested in chapter 8 of Autocontrol of Kevin Kelly, and in particular on a sentence in which he commented on a NASA experiment. And he said what was needed was a little autocontrol. In particular, this experiment is a kind of sphere in which algae and shrimps live and actually create an ecosystem that could survive, but somehow cannot evolve and generate new type of life or new ecologies because it doesn't have an exchange. It doesn't have an exchange with the outside. And what Kevin Kelly meant is that doesn't have a little autocontrol.
Yeah, the idea is quite interesting. This is actually, by the way, a commercial piece or product you can buy. And what is interesting of that is that besides being an extremely interesting experiment, it shows what the kind of reductionist approach means. Like reducing to the minimum the amount of components that can sustain life. And in a way, the idea behind that is to be able to control these elements better. But on the other hand, as you know, we found out, without a kind of critical mass of communication, of exchange, life just doesn't manage to develop. And somehow this kind of little out of control was brought years later by this man John Hallen when he actually developed this project Biosphere 2. And I think what was interesting of this is beside the scale, which went from a small product to a kind of large greenhouse, basically the idea was to have a completely different approach to the idea of creating an enclosed self-sustaining system. And in this case, the approach was to try and fit inside of this enclosed system as many, let's say, components as possible, so to have as much biodiversity as possible. And then somehow let the system sort out by himself all the web of connection to sustain his life.
But without really designing this interaction in a way, no? We found then another experiment on algae that somehow he connect to the NASA one to us. This is at MIT, and apparently on the roof of the MIT, maybe Carlo can confirm, there is a machine that works with algae and is kind of recreating a small algae farm. In this sense, it is connecting probably with the building of the MIT underneath, exhausting the CO2 and then being able to produce energy. But we somehow don't see a lot of architectural integration on that. I mean, there is a connection, there is a link, but there is no a kind of dialogue or architectural integration. So, inspired by that, what we did, the first experiment we did, we just built a screen on the office of our on the window of our office, and in which we try to work with algae, but at the same time to try to create an architectural device.
So basically, the first steps of the project were really to kind of expand the properties of this kind of living system, of living organism that would be on one side visual and effectively architectural in this case, being integrated in architectural component. But on the other hand, which is what sort of came later in this project, introducing a kind of direct engagement of people and users, if you want, which would not only be part of the space, but effectively be one of the components which generate the space, or influence the evolution of the architectural device. So basically, to sort of summarize in more simple terms, the STEM cloud machine works in relationship to these three, let's say, feedback loop. This three main feedback loop, which is the one that controls organic growth in relationship to the radiation field, and the one that controls organic growth in relationship to oxygenation and carbon sequestration, and finally interaction in relationship to the memory of the machine itself.
So interaction and oxygenation. Of course, in the gallery, we kind of set up a sort of experiment, and we didn't work with CO2 in the city, but we rather define an interaction of the user of the gallery that will become the provider of the CO2 and the one that will trigger, together with the light and the nutrients, the photosynthesis, and therefore the creation of this bubble of oxygen that will travel through the installation. Yeah, you see.
Yes, it is interesting to notice how, for instance, in this first cycle, the blowing condition, which in this case was, let's say, directly operated by the lungs of the people, like blowing the CO2 from inside their lungs, effectively saturating the bioreactors, which we will later see how they were created, and triggering a sort of evolution in what was happening inside of each bioreactor, growing algae, but then eventually also taking rather different route in what kind of algae, what type of
evolve in a different way according to the three parameters that we will later explain. So therefore you will have green algae or red algae.
And in the little diagram above, which is again like an extract from this flow of information, always sort of try to remind us that the effects that we see there are effectively not just the product of one simple action, but effectively is because of the interconnectedness of the various levels that such diversity can emerge. The oxygenation, so where like the process of algae generating oxygen through photosynthesis, and as you can see the little bubble.
Yeah, this is an effect we observed in the first installation, that there were this bubble traveling through the installation according to the exposure to solar radiation, basically.
And then effectively trying to observe the sort of architectural effects that all this bubble can create. So in the first installation, effectively we try to generate what was like a sort of interior landscape, whereby all these screens were kind of spaced in a way that would begin to generate sort of intense area of oxygen in between themselves. And in the installation we brought, or we developed for Civil, we can see instead the kind of site specificity of the system becoming stronger in a way, and sort of developing a kind of channeling path within the room, and then a small cocoon, which you can see basically the base would channel you through this landscape, and then eventually wrapping you in this cocoon of oxygen.
So basically, we conceived the various components of STEM as small bioreactor, and there was a whole process to investigate how they got built in a way.
Yes, obviously there were two main conditions there. One would function as a container of water and algae, and like a sphere, one we saw at the beginning, but
While-
on the other end,
When on the other end,
brick.
they will be bricks. So we started to test different geometry of bricks and how they could interlock one with the other. This is another part of the project. And therefore, we started to model in 1 to 5 to understand how they could really interlock, maintaining anyway a geometry that would allow the interaction, or that would be the geometry that we had defined to allow the interaction. And then we went in 1-to-1 prototype and the final one.
Yeah, so effectively, like what was interesting between like the initial example of the sphere and our intention of developing a wall system, effectively our screen system, has been sort of evolved through this the parametrization of the bricks itself. No? So the tension between the sphere itself and the brick was developed and then achieved this final configuration, in which in fact on one side we had a kind of potential for interlockiness and therefore like a sort of a wall condition, but on the other side let's say the tips of the brick were allowing for interaction and the diffusion, absorption and diffusion of oxygen and CO2.
So basically this small diagram explain how the water and the people could interact with it and how the geometry works. So on the top you have this concave part that would allow the brick to interact, but at the same time will allow the people eventually to water the brick like you do with small trees or flowers in the house. And then there will be a series of fiber that would work with the interaction of the people and therefore with the CO2 exchange.
Yeah, in this case it was quite interesting. As we will see later in the presentation, the screen suddenly acquired a kind of direction, if you want, like an in and out. So somehow where the curvature of the screen would define the side in which people would be robbed and therefore encouraged to interact, whereas the other side would become the sort of source of light. But obviously the kind of ambiguity between these sides is quite interesting because it leaves open the possibility of site specificity and actualization. So the machine actually has a kind of direction, if you want, but then the way it unfolds in the specific space, it makes it working in one side or on the other.
So basically,
sorry, can you just go back 1 second? I think it's quite interesting to show this to actually system. Basically, when the main brick is where the water is held, the bigger container for like algae growth, but then there are these other these other sets of micro environments, which are hoses, as you will see later, which are the sort of breeding grounds, if you want. So they function on a much slower kind of regime, like temporal regime, if you want. And then inside of this one, the kind of cultures of algae, very intense nutrients, level of nutrients can be bred and then percolate into the larger system, where actually triggering all the differentiation that we see in the screen itself.
so basically, the whole screen system, we'll try to speed up maybe a bit on this, is being generated through the interaction with solar, on one side with user and CO2, but the other main parameter is the solar radiation. So in the first installation, the response to solar radiation or existing solar radiation was quite direct. You can see on the top there is the map of the solar radiation, and on the bottom there is the different gradient of a kind of performative ornament of algae that would redescribe the screen.
In a way, I think radiation is obviously one of the main engine of growth, and therefore one of the main engine on our machine. But somehow what became interesting after this first experiment was the sort of, if you want, computational or informational nature of the project. So we suddenly begin to see like each of the containers as pixels, if you want, and therefore like the way algae would respond and concentrate as a kind of flow of information. So that actually became you want to go on?
Yeah.
That became for us a kind of starting point to develop a series of tools and techniques which would go from basically mapping the radiation fields in the room and translating it into the kind of numeric input for our architectural device. So as you can see in the first installation, this was simply a kind of direct indexing of the space. But then in this new project, it became a kind of matter of regulation. So how can we intervene as designers in kind of regulating or in promoting the self-regulation of the system? and without obviously being able to control the way the system would evolve. And in that sense, this is one of the, for us, interesting point as well. How, for instance, the shading or the intensification properties of the system would somehow self-regulate. So where more light would come in, the system would become more opaque because algae would grow faster. How people would respond to that would also change this pattern, and somehow there would be a kind of evolution. So
basically, we were saying before, we set up an experiment. One component of the experiment where the people interact, and the second component where the wide spectrum artificial light, that we try to define where to locate them in order to set up a differentiated growth in the whole structure. This is about some of the studies.
Yeah, this is basically going more into the technical details of how, for instance, we use the grasshopper and radiance to develop a function that would allow us to understand the potential of growth in relationship to the artificial lighting. So like positioning the artificial lighting would give us a capacity to regulate or to manipulate the way the architectural system would develop. And then obviously direct testing, which you would see in the next sequence. Basically, this gave us a kind of real direct quantification of what are the kind of nutrients level that we could play with. So somehow the whole kind of system of predicting became a kind of way of defining quantity of nutrients to trigger the system, to start the process, and to make sure that the process would begin to interact and to interfere with the environment. And obviously that would lead to some kind of differentiation that you see very clear in these two images, but that was somehow out of control, if you want.
Growth and city. So basically, this is the experiment we've been setting up in the gallery, but somehow we've been also trying to investigate how this could relate to the city, and in particular, in this case, to the city of Seville, or yeah.
Well, in this case, obviously, like the idea of using water from the river, from the local river Guadalquivir, was a way of somehow creating a further connection with the kind of local ecology. But let's say that the kind of relationship with the city was probably explored more in depth into the project we brought to Venice, the Biennale of Venice, which we may just touch briefly here. And because in that sense, we sort of imagined this like microecologies to be actually developed in relationship to the Venice Lagoon. So using the Venice Lagoon as a kind of breeding ground, and therefore like imagining this system or this potential spread or proliferated across a much larger scale. And giving rise obviously to sort of very different potential organization like algae farming, urban oxygenation, lagoon condenser. Don't go into the detail, but you see that, wait a second, that you see that in the larger scheme of the lagoon, this different configuration could begin to take place. And then effectively we decided to develop kind of architecturally one system which refers quite directly with this infrastructure of the lagoon, which is called bricole. So effectively we developed a kind of our own system of cyber bricole, which you can see there. And I mean, there were like a group of 5 presented at the Biennale there.
We will skip this one.
Yeah.
Interaction and saturation. We are working with processes, and all the processes have point of saturation. So we will show this part a bit quickly because we are running a bit late, but we have been embedding in our system a series of ways to record this saturation and somehow to allow the system to evolve further from there.
So the idea to actually integrate a little sensor and an LED on the bricks would simply allow kind of clues of how much interaction would happen between people to each block to be fed back to the user themselves.
Unfortunately, we don't have a movie of this here, but what was happening is that like this red light that you see here there was a flash sensor that was recording the interaction of the people with the installation, and if you would not interact enough, the light of the bricks will start to get red and redder and redder. So I will tell you that there is no kind of enough CO2 in the brick, and you need to interact with that. So as soon as you start to interact, the light instead will dim off. No, so there will be this kind of pattern of red dots appearing across the installation and defining how much people would actually interact with it or would not interact with it.
So this is kind of simply adding an
A kind
extra flow of
And
information.
also somehow what Theo was mentioning as well, a sort of playfulness and in the interaction with the people. This is
Something that we obviously went through, and also should thank Nick for the help he gave us on this, like a series of tests and kind of setting up the whole system there. And I think one thing I would like to add to you know, the script went through very quickly. Maybe you can also slow
It's
down a
okay.
little bit. Yeah, because it's like 1 minute more, 1 minute less. So suddenly okay, the idea that basically this system could you know, respond based on the information of the previous days and on the ranking of each blocks, you know, so that would begin to give a kind of build up of behavior to the way the system responds, which is something that I think is worth mentioning, as is going to be part of investigation as well. So the memory build up is connected to a kind of quite simple database system, which would basically rank each block's let's say capacity to stimulate interaction. So that would be somehow shown in a kind of similar chart.
So the last bit that we are going to explain is the how the actual installation was getting actualized on site. We started to map the condition on the site and look at how people would actually behave on the site before the installation, even if this image shows the installation. So we set up a diagram of circulation, and in relationship to that, we try to devise a system that would allow people to interact in a different way with the installation, either in a fast way or in a slow way. So
yeah, so effectively this kind of little diagrammatic mechanism was allowing us to sort of sense the highest concentration of flow in the room, and therefore like respond with let's say a shaping of our kind of artificial landscape, which you can see here materializing, which would then allow for the proliferation of our little bioreactors. So you can see the landscape being formed and then obviously engineered and sections
machined.
nested, machined using honeycomb cardboard, and then slowly taking shape. That begin to then inform the way the little bioreactor would start to proliferate. And as you can see, the idea was really to, on one side, channel the flow of people on a kind of faster interaction track, and on the other side, really capture them
so that they
within
could
a kind of cocoon
enter the
space.
machine itself. You don't have an image of that.
And that's
here.
the way the kind of system.
Of bioreactor or bricks would interact with the surface itself.
Yeah.
So somehow we were talking before about different of light, different of nutrients, different interactions. So each brick has been or each bioreactor was engineered as a brick, but was also different from the other. We had a catalog of them according to the position in which they were and the way you would actually interact differently with it. So
the catalog shows here basically what, you know, the main modification really happened on the level of which brick was equipped with the interactive system, and the length of these hairs or these antennas coming out of the brick, which would allow for or stimulate more or less interaction, and then the different regimes of flow of the algae. So the one inside of the tube slower and more denser, and then the on the top the bricks which would hold the water into the base. And then obviously this being kind of prepared as a catalog and organized on
this
site.
image can show from one side the brick had this very short oozes coming out, and on the other side there was the long one, for example, with which you could interact.
So that again would relate to the previous cycles of organization of the base and in relationship to the site. So there is a constant tension, like both of the level of the actual living material, but of the way it kind of organizes and grows in a specific site, which in this case was the gallery.
Okay. So the future of STEM cloud, an evolutionary architecture.
Yeah, this is basically just a kind of closing reference to effectively the work of John Fraser, which to a certain extent, if you want, like predicted and work quite hard here at the IA in the 80s on the subject of evolutionary architecture. And somehow, in a way, we see some of these concepts, as you can see, registering interaction, capturing growth and material differentiation, and developing behavior as paradigm that we are kind of bringing inside of our installation, which hopefully kind of carries on the discourse within the kind of contemporary
and now
potential.
we are setting up a new testing bed of STEM in Ecologic Studio, and we are interested now to try to understand how, on one side, the idea of the testing bed and interaction with the people, but on the other as well, how we can become more integrated with the architectural system in a way, and exchange with other sources of CO2 as well, but that's next chapter.
Thanks.